I suppose I can just get started, right?
Yeah, go ahead. Yeah.
I'm imagining I'm in a seminar talk where I have to wait to be introduced, but you know who I
No,
am.
go ahead.
Okay.
Charlotte's going to tell us about algebraic theories and monads.
All
Woohoo.
right. Thank you. Um, okay. So, all right. So this is going to be a really, really introductory talk to algebraic theories. And I'm actually going to start by telling a little bit of a story of the history of these things. Okay. So first of all, back in 1935, Garrett Birkhoff wrote a paper which was the starting point for a new discipline within algebra, which is called either universal algebra or general algebra, depending on who you talk to. And this discipline within algebra deals with those properties common to all algebraic structures, such as groups, rings, Boolean algebras, Lie algebras, and lattices. Lattices are also order structures, and you might know them from combinatorics as a special kind of poset, but they also have an algebraic presentation. That's a totally algebraic way of thinking of them.
So one comment, the lattice in this sense is not the same thing as, say, the set of points on the plane with integer coordinates, right?
This is a poset with unique. So I'll just say it because writing it's going to be a little agonizing. By this lattice, I mean a poset in which every pair of elements has a greatest lower bound and a least upper bound, and those guys are unique. Okay. So the real numbers themselves form a lattice under the usual ordering. So do all partitions of finite sets under the usual ordering, and so forth.
Uh-huh.
Okay. So, all right. And so, and so do the subgroups of a group, the intermediate fields between two fields when you have an extension of fields, and so forth. All of these things are lattices. Okay. Thanks for reminding me of that, because I'm just going to start saying the word lattice to mean that thing and not mention it otherwise. Okay. Mm-hmm. So Birkhoff used lattice theoretic in the sense of order theory ideas in his paper. In 1940, he published a book on lattice theory in the sense that I just vaguely described. Now, Oystein-Orr referred to lattices as structures and led a short-lived program during the 1930s where lattices were hailed as the single unifying concept for all of math. And I only mention this because of his influence on Saunders MacLean and how category theory did ultimately sort of take on this aura of being the single unifying concept for all of math, if you had to choose a mathematical discipline with that title. Mm-hmm. So during that same period in the 1930s, Saunders MacLean studied algebra under Orr's advisement. MacLean went on to become one of the founders of category theory and also co-authored an influential algebra textbook with Birkhoff. So over the next few decades, universal algebra and algebraic topology, because remember that MacLean was an algebraic topologist, algebraic topology and universal algebra grew into decidedly separate disciplines. And so it was no longer the case that people who knew about one knew about the other. They had become their own separate things. And so by the 1960s, Bill Levere was a student of Samuel, or I think as Doug calls him, Sammy Eilenberg. Yes. Who was another one of the founders of category theory. And although most of Eilenberg's students were algebraic topologists, Levere wrote a thesis on universal algebra. Apparently, Eilenberg famously did not even read Levere's thesis before Levere was awarded his PhD. Eilenberg did finally read it in preparation for his lectures on universal algebra and the theory of automata at the 1967 AMS summer meeting in Toronto. And now that I think of it, I'm not sure why there was a summer meeting in Toronto. Does the AMS include like Canadian? Is there not a Canadian Mathematical Society? Anyway, it doesn't matter. Okay, so and I actually said I might talk about more computer science applications of these things, but I think I already have more than enough to talk about. So I just will mention here that there are computer science applications of the things I'm about to talk about, but I'm not going to get into them today. And those applications were recognized quite early on. So this talk is on the category theoretic treatment of universal algebra, which was the topic of Lever's thesis, and also his original treatment of algebraic theories. In that treatment, or the algebraic theories that appeared in that treatment are now referred to as Lever theories. Okay. So first, I'm going to talk about what algebras are in universal algebra. Of course, we already have way too many things called algebras, but here's another one. And then I'm going to talk about the concept of clones from universal algebra. Then I'll talk about equational theories. And once I have enough of this background set up, you will know, or at least have a picture of many of the things that Lever was thinking about when he first defined his algebraic theories. So then I can actually give you the definition of an algebraic theory and some examples, and the examples and the motivation hopefully will seem more sensible to you than if I just handed them down to you for no apparent reason. And then finally, I'll discuss a little bit of the relationship between monads and algebraic theories. But as I already hedged before, I'm not going to be able to actually get that far today. Okay. So what is an algebra in universal algebra? This is supposed to be some discipline within algebra, which is more meta than studying just groups or rings or other things by themselves. Well, the basic objects here, algebras, are built up from operations. Operations are rules for combining elements of a set together to obtain another element of the same set. So formally, we're going to take some set A and some whole number. I know this is evil, but I'm going to denote by W the set of whole numbers, which is 0, 1, 2, and so forth. So please just bear with me. That's what many people call the natural numbers. Okay, and so a function taking n tuples of elements of A to A is called an n-ary operation on A. We also say that f has arity n. And note that n is allowed to be 0. And so if you'd like to think about what the 0th direct power of A should be and what maps from it to the set A look like, then that's a good exercise. Also, I'm always going to assume that this underlying set for an operation is non-empty. We usually don't want to think about the empty set as the universe for an algebra. Okay. Oh, and also please stop me if there are any questions. Of course. Oh, I guess Doug already did. Okay. So algebras are sets with an index sequence of operations. So a universal algebra, or just an algebra, is a set A equipped with a sequence of operations, big F, which is a bunch of little fi for i's coming from some index set. Right. So that's an algebra, a set with a sequence of operations, which are indexed in this manner. So if we have some algebra, oh, well, I guess, okay, I don't want to belabor it too much, but this includes the usual familiar things that I mentioned before, groups and rings, and perhaps other things like lattices, if you can view those as algebraic structures and so forth. All right, so given an algebra, we can define a map rho that takes our index set to the whole numbers, or the non-negative integers, in other words, where rho of I is the arity of the ith operation for this algebra.
Where rho of I is the arity?
Yeah.
Like AIRITY or something?
Oh, yeah. So
What is arity?
so back here, I said that if you have an operation that takes n tuples of things in A to A, then that's also referred to as an operation of arity n.
All right, I missed that. Thank you.
Yep, no problem. So for instance, the multiplication in a group is a binary or two-arity operation. So the arity of the group multiplication is 2. Okay. So actually, okay, for an example, if we take our algebra A to have a set of elements Z, all of the integers, and then 3 basic operations, which I won't write as a sequence in this way because it's exhausting. Let's say I call those operations F, G, and H, where I think of F as the group multiplication, and then G is the inversion, and H is the identity operation. Then the signature then this corresponding signature would be 2, 1, 0. Okay, so now I'm saying like FGH instead of F1, F2, F3. But if you wanted to write it that way, we'd have row of 1 equals 2, row of 2 equals 1, and row of 3 equals 0. Okay, maybe that was a little distressing to switch notation like that. So like F1, F2, F3, and you can label this as a single sequence if you like. Okay, so this map that assigns to each index the arity of the corresponding operation is called the similarity type of the algebra. Oh, and so then this algebra A that I've labeled here would be the integers, and we can think of F1 as the usual addition on the integers. So maybe a more prosaic way to write this is Z plus this minus means taking the additive inverse, and then we can put 0 here to indicate the identity, the additive identity element. Okay, so maybe that's a more familiar way of writing it. All right, in any case, this map is called the similarity type of the algebra. And so we often say the similarity type of a group is just 2, 1, 0, is that sequence of integers. So when two algebras, say A, with some underlying set A or some universe A, we say, and a sequence of operations F, and some algebra B, this is like a bold B, with underlying set B and set of and sequence of basic operations G, when these guys have the same similarity type, we say that A and B are similar algebras. And usually you only want to talk about similar algebras when you're discussing anything in algebra. We don't usually think of homomorphisms between groups and rings, for instance, because those things don't have the same type. I mean, of course, there are group rings and you could perhaps define something in that case, but in general, one can imagine that there isn't really a sensible way of handling algebras of two different types simultaneously. I don't really want to talk about things like homomorphisms between Lie rings and, well, maybe I do. Okay, there are lots of relationships, but generally speaking, I want things to have the same similarity type. I want to talk about homomorphisms between two groups, not between like something like a group and a ring. Okay, so speaking of homomorphisms, the definition of homomorphism of algebras is exactly what you would expect. If we have two algebras with the same similarity type, then a function taking the underlying set of the first algebra to the underlying set of the second is called a homomorphism from A to B, when for each basic operation, so for each index I, and any tuple of the appropriate size from A, we have that H that we can, okay, I'll say it this way. This is the good way to say it. You can either take that row of I tuple of elements in A, multiply them according to the ith operation, Fi, and then use H to send that over, or you can send each of those elements over by themselves and then multiply them in B according to the corresponding operation Gi. And notice that these indices I are the same. And this should be relatively natural if you already understand the definition of homomorphism of groups or rings or other things. It's just a generalization of that. Okay, so the class of all algebras of signature row, which I'll denote like this, can be taken as the objects of a category, which I'll denote by bold alg sub row, whose morphisms are algebra homomorphisms. So if I take any signature row and I look at all of the algebras of that fixed signature, then there's a corresponding category of those things whose morphisms are the algebra homomorphisms. So that gives me a nice infinite family of categories that I can play around with. So the category algebra has some well-behaved full subcategories. If we consider those classes of algebras K, which are closed under taking homomorphic images, so in other words, quotients, or which you can think of in the categorical sense as being like the images of epimorphisms. Okay, so if we have a class which is closed under taking homomorphic images, subalgebras, which are going to be sub-objects in the category theoretic sense. Although you can also define this directly in the manner that you would guess from group theory or ring theory. It's going to be a subset which is closed under all of the basic operations. And products. And this, of course, you can also define categorically, but the definition should be relatively obvious from elementary abstract algebra, because the product of a collection of algebras should have elements which are tuples, one from each of the corresponding algebras, and then the operation should all be performed component-wise. And so we still have time to talk about other things. I'm not going to belabor those too much unless people want to hear more specific detail. But all of these concepts can be defined concretely and are also their corresponding categorical concepts. So these words are being used appropriately. Okay, if there are no questions, then I'll finish my sentence. If we have a class of algebras K, all of the same signature row, which is closed under these three things, homomorphic images or quotients, subalgebras, and products, then we say that that class is a variety. I also want to mention, not that we'll get much into it, this products includes arbitrary indexed products, not just binary products, but even uncountably indexed products. It's necessary. Okay, so then for any such class K, which is a variety, I can consider the full subcategory of the category of row algebras whose objects are from that variety, and that's that variety viewed as a category of algebras. So examples of varieties include groups or abelian groups or quasi-groups or semi-groups. That would be 4 different examples. And also rings or unital rings or commutative rings or unital commutative rings or Lie rings and so forth. And also similarly for lattices, there are several different varieties of algebras which are canonically associated with the concept of a lattice. In the sense that I was talking about before. Fields do not form a variety. This is straightforward to see. Take your favorite field, take the direct product of it with itself, then you're going to have elements which are not invertible. Or you're going to have, you're going to have 0 divisors. So the direct product of fields is not a field, and so fields do not form a variety. Rings do, though. All right, now I'm ready to talk about clones. So we're going to want to keep track of all of the functions which can be built using the basic operations of some algebra. And so if I have some whole number n, some non-negative integer, and a set A, which I always assume is non-empty, then I'm going to denote by op sub n of A the collection of all n-area operations on A. So this is just the collection of all functions from A to the n to A, which we also might just denote by set of A to the n to A. So if I have 2 whole numbers, n and k, I have some n-area operation f and n many k-area operations, g1 through gn, then there's a generalized composite of f with g1 through gn, which is itself a k-area operation on A. And that composite operation is defined in the following manner. If I want to feed this thing a k-tuple of elements, x1 through xk, what I'm going to do is I'm going to, for brevity, denote this by as a tuple x, and I'm going to plug that tuple into g1 and g2 and so forth up through gn, and then I'm going to form a vector out of those, or a tuple out of those, and feed that into the outside function f. And notice that since each of the gi or k-area and f itself is n-area, the sizes of each of these tuples is appropriate, and this is a well-defined function. Okay, so the collection of n-area operations on A must contain all of the coordinate projections p n k, which take an n tuple x1 through xn and pick out the kth coordinate. All right. So now a clone is a non-empty set, given a non-empty set A, a clone is a set C of operations on A, which can be of any arity. which is closed under generalized composition and also contains all of those coordinate projection operations, P and K. So the largest clone on a set A is just the set of all operations on A of any arity. The smallest possible clone is the clone which just consists of the projection operations of just all the coordinate projections for all possible n and k. So I won't get into this right now either, but clones are examples of operads whose operation spaces are just the discrete set of n-ary operations for whatever n you choose.
Are you going to define operad?
No, I'm just throwing this out just to mention it for those who know, but I'm not going to get into operads.
Okay.
Is that acceptable?
Yeah, sure.
Okay. I would like maybe another time, right? But okay. Okay, so now I'd like to define terms. So if we have a similarity type and a set of variables, oh, and I guess I should mention at this point, why am I starting to do this now? I'm trying to build up to talking about free algebras, which will come up later when I discuss the relationship between algebraic theories and monads. So that's what I'm assembling now as a preview. So if we have a similarity type, a set of variables x, and some set, which we now think of as a collection of abstract basic operation symbols. In other words, fi is now no longer actually an operation. It's just a formal symbol representing an operation. Okay, just a formal symbol. A term in this language row in the variables x is an element of the set t row of x, which is built up in the following recursive manner. So t naught is the original set of variables along with all of the null array or zero array operations. We think of an operation of arity 0. So if f is some function from a to the 0 to a, then we think of this as just a constant because this is a map from, well, a to the 0 is the collection of all maps from the empty set to a. That's one way to formalize it, which is going to consist of a single function, the empty function, which I can also view as the empty tuple, which has just no entries, so just a pair of parentheses. That picks out exactly one element of a. So f eating the empty tuple is just some element of a. Oh, I don't want my a's to be too ugly. And that we can think of that as a constant. So the initial stage of this thing, t naught, is just all of the variables that we want to use and all of our constant operations that pick out elements of a. Now, if we have some number n, then we can set tn plus 1 to be the previous stage of this construction, along with all of the formal generalized composites, fi composed with t1 through tk, where this fi is a symbol that we think of as representing a k-ary operation. And each of these t1 through tk are terms from the previous stage. And so we can build up terms with a set of variables in a particular language in this manner. They're all of the appropriately composed formal expressions with respect to these operations of the assigned arities. Okay, so that is, and I wrote it again here, t row of x consists of all the valid formal composites of the basic operation symbols whose arities are given by this signature with variable arguments coming from the set x. Now, if I have an algebra A of signature row and some term over the variables x1 through xn, we can define the term operation, which we denote by t to the a power, where this is the algebra A in the superscript, which maps n tuples of things in A to elements of A, where n is the number of variables. And we can do this by interpreting all of the operation symbols appearing in T as actual basic operations of A in the obvious way. And I won't write this down because it's going to be a little too much, and this example should suffice. So if row is the usual signature for groups, that was the thing that I wrote before, which I said had was signature 210, which we think of as binary multiplication, unary inversion operation, and then the 0 is a null array or constant operation that picks out the identity. So in that signature, we have that x times y multiplied by x inverse times y inverse. This is a term in the variables x, y, and that's just a formal string of symbols with respect to this signature and these variables. There is an actual commutator term operation though, and that's the thing I'm talking about here, because this formal expression is like the commutator of x and y. So there is an actual commutator term operation on the symmetric group S3 of permutations of 3 letters, which is a binary operation on the set of permutations. In other words, even though this xy, x inverse, y inverse is just an appropriately composed formal string, that does induce an actual function that maps pairs of permutations to another permutation, namely the commutator of those 2 permutations. Okay. So now each algebra actually has a clone associated with it. And that clone is the union of all of these little clo-n's of A, where clo-n of A is all of the term operations of arity n that are induced by terms in the appropriate signature for that algebra. So that's essentially all of the n-ary operations that you can make by composing the basic operations of the algebra in some manner. Oh, and that's also what I just wrote here. This is to say that the clone of A consists of all the operations on A, which can be built up using the basic operations of A. Oh, and implicitly we're using projections just because we want to be able to plug in, say, multiple copies of the same variable. We want to be able to produce things like the term operation on a group corresponding to x times y times x, for instance. And here we're implicitly using projections to get 2 copies of the x. So another way of saying this is that clo of A is actually the smallest clone in the lattice. And here, remember, think poset, special kind of poset of clones on A, which contains the basic operations of A. Okay, so now I'm ready to talk about equational theories. And then after that, we can finally get to algebraic theories. So to each ordered pair of terms in some number of variables, and some signature row, we can associate a proposition, just a formal proposition in propositional logic, called an identity in the language of row, which is this proposition. For all x1 through xn, we have that t1 of x1 through xn is equal to t2 of x1 through xn. Okay, and so this itself is also just a formal proposition in some formal language, which we denote more succinctly in universal algebra by writing that T1 of the xi, and then this does not mean approximately. This is just a universal algebra bit of jargon, which, as long as these things are discrete, should not cause us any worry that we'll confuse it with something being approximately something else. Okay, well, in any case, yeah, so this, we often just denote this with this squiggly equals, which does not mean approximately, this formal expression. And then we even roll write just T1, T1 is equal to T2 in this sense instead. Now, if we have a row algebra A, so it's an algebra of signature row, and some identity, which I'll just denote by epsilon, so perhaps epsilon is this identity, then we'll say that A models epsilon and write A models epsilon in this way when for all possible assignments of the xi to actual values within the set A, we have that the first term operation interpreted in A applied to this tuple x is actually going to attain the same value as this second term operation in A applied to this tuple x. And so that's what it means for an algebra to model an identity or to satisfy an identity. Okay, so now an equational theory is going to be the collection of all identities. Okay, so I should back up. So if we have a class K of algebras of some signature row, then we're going to refer to a set of equations of the following form. It's the set of all equations epsilon, which are modeled simultaneously by all members of this class K. We're going to refer to that as the equational theory of the class K, or as an equational theory. So this would be the equational theory of the class K, denoted by ID of K for identities satisfied by K. So for example, when K is the class of all groups, we have that the equational theory of K contains identities like x times y, z inverse should be the same as x times yz inverse. Similarly, because remember, also remember, these are all just formal strings of symbols, right? So they must have parentheses associating them somehow. You can't just write x, y, z, that's nonsense. And also, the same equational theory of groups would contain the identity x times e x inverse is the identity element of the group. But the same equational theory would not contain that, for example, x and y should commute, because that doesn't happen in a typical group. And it also wouldn't contain something like x times x times x is the same thing as x, because it's not in general true that a group element has order 2. Okay. So we similarly have equational classes. If we have a class of row algebras, then we're going to say that that class is equational when there's some set of identities, which we can think of as pairs of terms in the appropriate collection of terms, so that, okay, this is bad here. This is supposed to be, the class of all models of the set of equations sigma. That's what was supposed to be there. The mod didn't show up, so I made a mistake. So if it turns out that a class K is the collection of all algebras which models some collection of identities sigma, and so what this A models sigma means that for all identities little sigma in the collection big sigma, we have that A models that identity little sigma, which perhaps is kind of obvious, but in case it wasn't, there it is. So if we have a class of row algebras, which are all of the models of some set of equations or identities, universally quantified equations, then we're going to say that that class is equational. So all of the varieties that we have mentioned are equational classes by definition. There's an equational definition of groups, of rings, of commutative rings, and so forth. Those are all defined by some set of equations, some finite set of equations even. So it's actually pretty trivial. I suppose I'll be aggressive and say it is trivial to see that any equational class is a variety, in the sense that any equational class must be closed under taking quotients, subalgebras, and arbitrary, even uncountably indexed products. The converse is not trivial to prove, but it is true. And so this is the theorem of Birkhoff, I think 1935, very early on. It may have been the first paper, I'm not sure. That a class of row algebras is equational if and only if it is a variety. And so actually those two different concepts, one of which is more structural, this concept of a class being a variety, has to do with essentially even categorical properties that that class possesses, whereas the concept of being an equational class is much more about the identities that are satisfied, so the semantic properties that the class satisfies. But it turns out that these two concepts are actually the same. Okay, so for any collection of algebras which are closed under taking quotients, subalgebras, and direct products, where quotients is interpreted as epimorphism, so anything isomorphic to a quotient in the more elementary sense, then that class is actually defined by some set of equations, which may be infinite, but still exist. Okay. So now recall that any variety of algebras V is going to be a full subcategory of the collection of all row algebras. And so there is actually a forgetful functor which takes row algebras to the category of sets, where and I apologize, this F, remember, is denoting the collection of basic operations of the algebra. And so I'm not going to use it to denote the free whatever functor, which would be an adjoint to this forgetful functor. So if we have an algebra with some set of elements A and some basic operations F, the forgetful functor is just going to send that algebra to its set of elements, as is the case with the forgetful functor from groups to sets, for instance. So this functor has a left adjoint, and this H is what I'm going to use to denote the free algebra for that signature, and so, or for that variety. Oh, just for that. Ooh. Yeah, this is bad. Okay, so there is such a forgetful functor. There is such a forgetful functor, but actually what I wanted to say is that if we fix that variety V, which is a full subcategory of the category of row algebras, okay, we still have a forgetful functor, which is defined in the same way, namely take the underlying set of the algebra. And that functor has a left adjoint. Even if I restrict to just the full subcategory V, that restricted forgetful functor still has a left adjoint, which is not obvious, right? That's not something that trivially follows. If the bigger category has it, the smaller one doesn't have to. But in this case, there is still a left adjoint. And I meant to write V here as well, which assigns to a set the free algebra H of X, or maybe I should write it HV of X, on generators X in the variety V. And this free algebra functor can be constructed quite explicitly, actually. And this also, by the way, is a generalization of the construction of the free group on a set of generators. We can take this, and so again, this H is depending on the variety V. So the free algebra in the variety V on a set of generators X it's going to be a quotient of some algebra. Okay, so what is this algebra that I've denoted by bold T sub row of X? Well, the elements of that algebra are going to be terms in the signature row on the variables X. We've already defined those. Those are just all of the appropriately composed formal expressions in this signature. And then we're going to have some set of basic operations F. And essentially what we'll do is the following. If we have some basic operation Fi, and we want to feed to it some number of terms, T1 up through T sub row of I, where row of I is the arity of this operation, then we're just going to define that to be a new term. And that new term is just the formal composite of F with each of these TIs. And so, in other words, applying this operation to some collection of terms just means formally compose that operation onto that set of terms. And so that's relatively easy to write down, but if you look at what it is even for groups, for instance, it's a quite wild thing. This is just the free algebra on that signature. And so if you do the corresponding thing for groups, it has some crazy non-associative multiplication. It has a unary inversion operation, which has no actual nice properties at all. And it has just some formal identity element, which doesn't obey any of the properties that an identity element should. Okay, so that's a pretty wild thing, but relatively easy to write down. And what we want to do is think of that as an algebra, as an object in the category of row algebras, and we're going to form a quotient of it. So I haven't talked about this at all, and I thought that I wouldn't spend too much time on it. But what we're going to do is actually quotient out by an equivalence relation, which is compatible with the operations. And so there is a notion in universal algebra, which I'm not going to formally define or get into, but if we have an equivalence relation on the underlying set of an algebra, which is compatible in the appropriate sense with the basic operations of that algebra, then we refer to that as a congruence. And so congruences are actually precisely the kernels of homomorphisms, in the sense that they're the equalizers of homomorphisms with themselves. And so just as you have that normal subgroups or the equivalence relations defined by them, the coset relations should be the kernels of group homomorphisms, and ideals or the equivalence classes of ideals should be the kernels of ring homomorphisms. So too is there a general concept for any sort of algebraic structure. And that's called the congruence. So the congruence we need to quotient out by in this case is what I'm calling theta v, and two terms, which again are two elements of this algebraic structure, will be identified in this equivalence relation precisely when the class of algebras, the variety of algebras V, models this identity that T1 and T2 are identified for all possible assignments of the variables. Okay, and so I'm not going to prove that this is the free algebra for this category of algebras, but one may verify that this actually has the requisite property. Okay, so are there any questions at this point, or? All right, we're still good. Oh, and then of course, again, if V is the class of all groups and this row is the signature for groups, then this thing HV of X will actually be the free group on a set of free generators X. Okay. All right, so now I'm finally ready to talk about algebraic theories. So if you have any questions on any of the stuff about basic universal algebra before I talk about algebraic theories, now is the time. And again, as a reminder, all of what I just described and more were things that Levere was acutely aware of when he was in graduate school in the 1960s. That was all at that point well established. Okay, so now Levere wanted to do universal algebra in a categorical treatment of universal algebra. And so he defined something like the following, although not precisely this. So for us, an algebraic theory, and this is, I guess, what's more standard now, is a small category. So there has to be only a set worth of objects, T, which has all finite products. Okay, so that's an algebraic theory. We're going to see eventually that there is actually a relationship between algebraic theories and the other concepts that we were talking about before, although it might be a little oblique at this point. Okay, so an algebra of an algebraic theory is going to be a functor sending that algebraic theory, which itself is a category, to the category of sets, which preserves finite products. So again, I apologize because there are algebras in universal algebra. There's algebras of algebraic theories now, and there are also algebras associated to monads, and there's just algebras all over the place that aren't at least necessarily obviously the same thing. So an algebra of the algebraic theory T is just a finite product preserving functor from T to set. Okay, so the category of algebras of an algebraic theory is going to be the full subcategory of the category of functors from T to set whose objects are algebras of this T has become weird for some reason. This should just be calligraphic. Oh, that looks like a tau. This should be this calligraphic T that I struggle to write by hand. Okay.
Math,
and so remember, I'm sorry, what?
Say math cal T, /math cal T.
Oh, I'm sorry. The calligraphic T is math script T. That's right.
Well, which one do you?
I mean this one.
I know.
That is math cal T.
Yeah. Right.
Yeah. Okay. Thank you. Yeah. Yeah, I guess because the math. Well, okay. I'm not going to worry about it now. Thank you. Okay.
Math script is a much more flowery font.
Yeah. Oh, okay. Yeah. Yeah. So is calligraphic the right word? I always thought the cal was for calligraphic.
It is.
Oh,
Yeah,
okay.
Math Cal, there's Math Cal and there's Math Script. They're two different fonts in tech, and I believe this is Math Cal.
It is, yeah. Okay, so this is calligraphic. Yeah. Okay, thank you. Okay, so we're going to refer to now, okay, so now we're going to refer to a category which is equivalent to the category of algebras for some algebraic theory T as an algebraic category. And so, of course, at this point, I've already hinted, and you must, be thinking that this must have something intimately to do with those categories I defined before, which were varieties of algebras. And indeed, these things do have to do with each other. But let me start off with an even simpler example first. So the most basic, perhaps, example of an algebraic category is the category of sets itself. And so we can take, we can actually see that set is equivalent to the category of algebras for the algebraic theory W, where W is going to be the following category. So W is the full subcategory of the opposite category of set. So not set itself, but the opposite category, whose objects are all of the n sets for any possible a non-negative integer, a whole number, whatever, n. Okay, we really don't care that much about 0, so throw it out if you want to. All right, so we're going to take W to be this full subcategory of the opposite category of sets. And now notice that because we're in the opposite category of sets, if we have a functor from W to set, then okay, if that is actually an algebra, which again means finite product preserving, it's product. Okay, so finite product preserving, the image of the set n, the n element set n under this functor, well, okay, so this n is it's the coproduct in the category of sets of the singleton set with itself n times. But because if I'm taking the opposite category of set, coproducts in set are products in the opposite category. And so this is the same thing. So these products, these x's for products, are denoting the product in set op, which is actually the disjoint union of sets. And so this is the image under the functor A of the product in set op of n copies of the singleton set with itself. But since A is supposed to be an algebra of W, then that means that this is the same thing as A applied to the singleton set cross A applied to the singleton set, blah, 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 where this also occurs n times. So the functor A, okay, at least on objects, the functor A is determined by the image of the singleton set, 1. All right, so more questions? Oh, maybe? Okay, that was just a microphone thing, okay. All right, so now, as I said before, this functor A is determined by the set, which I'll call little a now, which is the image of the singleton set under this finite product preserving functor A. So a morphism from the set of n elements to a singleton in the opposite category of set is a function from the singleton set to the set of n elements. So that's essentially just picking out a single element from the set of n elements. So if we have a morphism, f taking n to 1 in the opposite category of set, then we have that its image should be actually a function in set taking n tuples of elements of A to elements of A. In other words, the image of a morphism, f in the algebraic theory W, should actually be an n-ary operation on the set A, which is the image of the singleton under the functor A. And so if we think about this a little bit, we can see that actually the set of all projections the set of all projections from an n set. This is what I want to say. So remember, we have a clone of projections on a set A. So the nth level, all of the n-ary operations in the clone of all projections on A is actually the same thing as the image under this functor A of all morphisms from n to 1 in set op, or we can also say in W if we want, since we're taking W to be that full subcategory of set op. And so actually what we've captured here is that the Hom set from A of n to A of 1 is actually just the same thing as the nth, all of the n-ary operations for this particular clone. And so this is where now clones are coming back in. All right, and so the reason for this is essentially that if we have a map that sends, let's view this singleton set as the set containing just 0. 0 has to get mapped to something, call it I. Then, so then essentially what is happening is that, so in the category of sets, each of these maps that sends 0 to I, each of those maps is one of the canonical inclusions that witness that this thing is actually the co-product of this is actually the co-product of a whole bunch of copies of the singleton set. I equals 0 to n minus 1. Right. So each of these maps is actually one of the canonical inclusions that show that witness that this is the co-product of a bunch of copies of one. And so then when we look at the opposite category of set, these things are now witnessing that this object is also this object there is the product, and they should become the corresponding projection operations. And so that is essentially what is happening here. And so then this is telling you when you choose a particular set to send the singleton to, this is telling you this map that sends 0 to I in the set of n elements is now telling you you should take your tuple and project onto the ith coordinate. Okay, so I know that that's a little backwards, but I hope that seems reasonable. I mean, there's a lot of swapping going on between the opposite category of set and set itself. All right, so we've at least at the very least, we seem to have captured the concept of the clone of projections on a set with this algebraic theory that I call W. All right. Oh, and I should mention that the category of sets itself is actually a variety of algebras with no basic operations. So algebras are generalized sets, which also carry operations. And so this is sort of the simplest version, where a category of algebras is equivalent to a category of algebras in the universal algebra sense is equivalent to the category of algebras of an algebraic theory in the category theory sense. Okay. So now let's look at a slightly different example, which is more interesting. We're going to take group to be the category of all groups. And so we actually have that group is equivalent to the category of algebras for an algebraic theory G, where the objects of this algebraic theory G are still just canonical sets of n elements, 0, 1 up through n minus 1. And we're going to define the Hom set from n to 1 in G to be H of x1 through xn, where this H is the free group functor that I described previously in the more general setting of just some variety of algebras. Now, I'm being a little bit abusive with my notation here because this H is actually a functor. And maybe if I was being really careful and pedantic, I would have made this a bold H, which I also will denote by underline when I'm writing by hand. And then this thing is not the free algebra itself, because the Ham, the collection of morphisms from n to 1 in this category G should be a set, not a group. So by this, I mean the set of all elements of the group freely generated by generators x1 through xn. So that's going to be the Ham set from n to 1. And then because every object in this category, similar to the example we had before with the category W, because every object in this category is actually a product of the singleton with itself a bunch of times. This completely describes what the morphisms in this category should be. If we replace 1 with m here, we're just going to get m tuples of elements of the appropriately sized free group. And so then composition of morphisms is determined by composition of the corresponding terms in the free group by that generalized composition. Okay, so then a functor taking so if you accept that that is a category that I've sufficiently defined for you, then a functor taking this algebraic theory G to set selects an object, A of 1, which is going to be what we're thinking of as the set of elements of a group A. And I'm going to now abusively also denote by bold A specific group, whereas this bold A is actually a functor from the algebraic theory G to set. And so this has actually been set up so that the clone of all n. So if we look at all of the n-ary operations in the clone of term operations for the algebra A, remember each algebra had a clone associated with it, some huge collection of all operations that you could possibly define using the basic operations of the algebra. Well, it turns out that we've set this up so that there is a corresponding group A, so that the clone, all of the n-ary operations in the clone of A are precisely the images under this functor, this finite product reserving functor from this algebraic theory G into set. They're just the images under this functor of all of the morphisms from n to 1 in this category G. And so that is what you will obtain by unraveling definitions, assuming everything has indeed been set up correctly. Okay, so at this point, are there any questions? No, okay, or comments? All right, and so this was actually Lever's initial motivation, as I understand it, that he wanted to categorify what it meant to have an algebraic structure in the sense of universal algebra, so that he could start to treat universal algebra in a more categorical manner. Because of course we could define varieties of algebras, we could define categories naturally associated to varieties of algebras, but that definition wasn't really inherently categorical, whereas this definition of an algebraic theory as a certain category and then a category of algebras being finite product preserving functors is much more natural from the perspective of category theory. And so then the hope is that this generalization is actually going to be effective in guiding the study of universal algebra, and hence the study of specific algebraic structures like groups or rings or quasi-groups or Lie algebras or other things in a systematic categorified way. Okay, so to give you some more evidence of that, hopefully I'll just mention the connection with monads. But as I already said a bunch before, I don't have a lot now, so I really was just giving you the very, very basic idea of what this is about. But okay, so I'll remind you that a monoid in some category is an object M along with morphisms from M squared to M, which this means the direct product of M with itself. and also this E taking the terminal object of the category, which necessarily must exist in order for this to be defined, to M, where M is an associative operation with unit E in the sense that the following diagrams commute. Okay, so that's just a monoid object in some category. Now, similarly, a monad is essentially a monoid object in the category of endofunctors of some category C, except we're not using direct product now, we're using composition. So maybe not literally what I just said, but at least quite close to it. So now a monad has some endofunctor M taking the category C to itself, and natural transformations taking this MM is the composite of M with itself. Since M is a functor from C to C, we can apply it twice to M, and eta, which takes the identity functor on C to M. And so we want essentially that mu is an associative operation with unit eta in the sense that the following diagrams commute, which are just the diagrams that I wrote down before, where this is associativity and this is both of the left and right identity properties. Okay, so that's just a reminder. I'm not going to do the whole theory of monads again now. So any variety of algebras V can be viewed as an algebraic theory analogous to the example with groups, which we gave before. Now, we can actually define a monad, and I guess I'm being abusive here, calling M the monad. We have to have a unit as well, but we have a functor from set to set in any case, induced by the free forgetful adjunction for V. Remember before I accidentally wrote down that there was this free functor that was adjoint to the forgetful functor for variety V, but I accidentally wrote down algebra at first, and then I made a comment that said, oh, well, actually this is the forgetful functor adjoint to a free functor, both for the category of algebras V, just in some variety V. And then, so each of those gives you an adjunction. Each possible variety gives you a different adjunction, even if you have two varieties of the same signature. And so that's actually easy to see for groups, for instance, because for abelian groups, there's the corresponding free abelian group generated by a set of generators, but the free group on that same set of free generators would be a much bigger thing, where the generators wouldn't commute with each other. Okay, so in any case, for any variety, we have a free forgetful adjunction like the thing that I described before. And so we can take our monad to be, remember this H is the free functor since I used up capital F already. And then this U is still the forgetful functor, just mapping an algebra to its set of elements. We can thus obtain from any variety of algebras, both an algebraic theory, similar to the one for groups that I described previously, and also a monad. Okay, and I've told you how to some extent, I told you how to do both of those things. I haven't told you what the unit is, but you can probably figure it out if you understand the example for groups. So it's possible to define equations and equational categories, which are analogs of equations and equational theories in universal or equational classes, I suppose is the appropriate thing. Equations and equational classes in universal algebra, there's a corresponding categorical definition of these things as well for algebraic theories. And so it turns out that equational categories are up to a concept of concrete isomorphism, preserving the forgetful functor, precisely the categories of Eilenberg-Moore algebras for finitary, and this word I haven't defined at all, monads on the category of sets. And so, okay, and so this is sort of the beginning of the correspondence between the concept of a monad and an algebraic theory, where we're able to, well, assuming that we actually go through doing this, that we're able to see that that these concepts are quite close to each other, that they are essentially different presentations of the same idea. And just as sort of a comment about the computer science side of things, part of the reason that you might want to look at Lever's treatment as opposed to the more common presentation of monads, is that in order to have a monad, you have to already understand what this endofunctor looks like. And so what's nice is that if you are given a variety of algebras, perhaps even just defined by some finite list of equations, it's possible for you to, in some sense, compute what the corresponding endofunctor should be and understand what that monad should look like from that situation. And so that different, maybe more verbose presentation can be useful perhaps. And so it's a different perspective that people have started to exploit more recently. Okay, so I think that pretty much sums up what I wanted to say. I started looking at this textbook, Algebraic Theories. The foreword to this was actually written by Bill Levere, and I found this on Doug's library of books and papers on his website. I always use for reference for universal algebra, Bergman's universal algebra. And I also took a look at the category theoretic understanding of universal algebra that was described by Highland and Power in this paper. Okay, so I know the end was a little vague, but I hope that you enjoyed the talk and at least have some picture of what Levere was thinking when he was writing his thesis that Eilenberg did not read at the time.
Well, thank you very much, Charlotte. Let's everybody unmute yourself. Let's do a hand.